Well, in the next, we will provide some technical details about the derivation of this inequality, where we upbound the maximally possible difference in the in-sample evaluation of a hypothesis that belongs to some family. So the maximum value of all hypotheses in the family of the differences. We will bound the possibility here using another possibility, which we refer to the difference between two different in-sample errors, also of the maximum difference of the hypothesis in the family. So first, let's establish that let's call this event that the maximum difference of in-sample and out-of-sample error evaluated on some data set. We take for each hypothesis of a family, we compute the difference on the data set, and the event is for the maximum difference. That means there exists one hypothesis, so that when it is evaluated on this dataset, the difference is exceeding the predetermined threshold. To talk it in everyday language is that this training data sample is bad, is unreliable for any of the hypotheses in the family. So the first step, it is natural that because we are talking about when the event happens, this dataset is somehow the most sensitive hypothesis will get a large in-sample out-of-sample error difference. Then we must be able to find this particular one. Let's call that HE from the hypothesis family. So when we evaluate HE on the training data sample, we will get an in-sample error that is very different from the out-of-sample error of HE. So it is natural when this event happens, we will be able to find such HE. So let's consider the consequences of having such an HE. Let's consider, how about if we take another training dataset. Okay, no, this dataset is different from the previous one, on which when we evaluate on that, our HE is evaluated inaccurately with respect to its out-of-sample error. Let's call that new dataset HD prime. Because HE was selected using the original dataset, and D prime, the new dataset, is independent to HE. They don't know each other. They are totally strangers. Therefore, Hofstad's inequality applies to this case. The probability, this probability is taken over the D prime. So from all the possible n-sample data and training data sets, if we sample one D prime, the probability that the D prime happen to be bad for this HE is protected by the Hofstad's inequality. So the n-sample error of HE differs from its out-sample error is larger than half of the preset epsilon is bounded by some threshold. Let's call that delta, which is the same to say the probability that the in-sample error and off-sample error, they are close to each other within this half epsilon is greater than 1 minus the delta. Because we know with more and more n, we can reduce the delta to very small value, which is equivalent to say we can push the probability that the evaluated in-sample error on D prime is close to the out-of-sample error for HE close to 1. So there must exist some n0 or some large enough integer number. When we take the training sample error number size greater than this number, we will have this happens with a probability of more than 50%. So this is a relax of the condition. This must be able to do. This is something we must be able to do. So summarize what we are arriving here. What we are seeing is, look, we are talking about from the H, we have a data D, and if we evaluate D on H, and we are talking about there is some very hypersensitive H, which is not going very well with D. For this HE, see, is out of sample error is here. When we evaluate this HE, the in-sample error of HE on the D located somewhere beyond the positive negative epsilon region between this E out of HE. So let's see, this is some golden standard we want to locate at, and this is the threshold we want somewhere in the green zone, but no, sorry, for this HE we happen to locate somewhere here. And then we are saying we are taking a new D prime, and because of the Hofstad's inequality, we will see if the n increase, we will have larger and larger probability, so that the in-sample error evaluated on D prime, let's call that E in prime, is within this positive negative half epsilon here. Okay. Let's call this event some C. And from this illustration, it's not difficult to figure out what we want to talk about. We want to see, okay, then there is some safe zone here. That's probably not a good illustration. Use okay, why this color is so funny? Just because this is a zone, this is a zone. This zone separates the evaluated E in and E in prime. These two must differ from each other more than half of epsilon. Let's call this B, event B. So D derives B, and now we are considering the event. The in-sample error of HE and in-sample error of HE evaluated on D prime is greater than half of epsilon, and because HE is a member of the hypothesis family. So this also implies that the most sensitive hypothesis, by sensitive we mean the difference between A evaluated on D and that evaluated on D prime, the difference is large. The largest difference between these two in-sample errors must be greater than half of epsilon. That is obvious because we already have one member in the family that have this condition satisfied. So we must be able to, the maximum one of the family must have this condition satisfied as well. So let's call this, now we do not distinguish too much about these two events. They are very naturally linked. Let's call that B prime maybe. Therefore, we can convert our discussion about the probability of A in terms of the probability of the event B prime. So if B prime happens with some probability, this probability, PB prime, then with twice as much of the probability, A will happen less than twice of the probability this way. So using the probability of B prime, we limit the probability of A. So what we have done here is we have an A, and then we use Hofstad's inequality this way. I said we can drive that probability to 1, but I'm happy to drive it only to half. So we cut half of A. Okay, in this half of A, this will derive that we must have the supreme of H in H, so that AN and AN prime, of course we are considering this H, greater than half of epsilon, and that is B or B prime. They are linked to each other. Because this derives this, then we will see the probability of this half, this portion of A, let's call that A portion, is upbounded by the probability of this. And because this portion is, for conveniency, we use 1/2, we said that the entire probability of A will be bounded by twice of PB prime. So that is our logic. Well, about the B prime, we can see that now we successfully removed the out of sample error E out from our plate. It's much more palatable. At least we are talking about some limited cases where we will be able to bound them if the hypothesis set is friendly enough. We will discuss these aspects in the following discussion.